So the first speaker of the day is Carl Crader. Carl Crader is working on a project with Professor Sriram Vishwanath from computer science. Unfortunately, Sriram is not going to be able to be here today because of last-minute conflict. But I'm going to start introducing Carl. Carl received a PhD in material science and engineering at UT in 2017. He's the Chief Security Officer of Griplus, a company that is focused on securely storing and spending digital assets. And up until recently, he was the Director of Energy at Consensus, developing energy business solutions using blockchain technology. Carl?
Thanks for the intro. Thanks for everyone coming this early morning. Not tremendous weather. But I'm Dr. Carl Crader, and today I'm going to be talking about not Grid Plus, but an idea that I came up with to address one of the two problems that I think are sort of blocking blockchain's mass adoption. First problem is usability, which is kind of one of the things that Grid Plus is addressing, but the second is scaling. So today I'm introducing publicly for the first time BlockReduce. So just to give a little bit of context and background on blockchain, don't know kind of the depth of the audience. So one thing that I always want to do is kind of sort of put the technology in context before talking about it so we kind of understand its place and its use. And in terms of blockchain as it exists today and many of the systems that give people exposure to blockchain, it really is analogous to what we'd call the application layer in the TCP/IP stack, such things as FTP, HTTP, and SMTP. The applications that have been built to date are kind of very poor in that the protocol itself is still vastly exposed to the end user, and they have to be familiar with it. They have to be familiar with security. And in short order, people are building applications that are now abstracting that, so we'll hopefully see things in the near future where instead of having to enter a web address, right, that's all, or having to enter an IP address, right, that's all abstracted sort of behind the scenes, and we just get this nice GUI that kind of lets us interface with these systems. But right now, most applications are kind of these very, very light sort of shells on what essentially is a protocol. The principal difference between this protocol and every other protocol, though, in my mind, is that blockchains aren't a mechanism for transferring information. Rather, they're a mechanism for digitally transferring value. So what is blockchain in sort of the, and how does it compare to the traditional financial system? It's interesting when people sort of get into blockchain, they get into cryptocurrencies for the first time. I think their sort of largest hurdle to understanding them actually has nothing to do with blockchains themselves, but has to do with their lack of understanding of the current monetary system and how it functions. But the more that you understand the current monetary system, the more that you understand the blockchain systems and the crypto systems that underlie them, the more parallels between the two you'll see. But let's just look at kind of banks versus blockchain. So blockchain is a shared, peer-to-peer digital ledger that we have nodes, and those nodes can check the ledger against a consensus mechanism. In the traditional banking system, we have institutions that have siloed databases that hold credits and debits and accounts. 95% of money today is represented digitally. It's not in any sort of physical form, such as cash. So these two things are pretty analogous. One of the differeyences, though, for the banks is that for them to essentially attest to the rules of consensus, they need to bring in these third-party auditors periodically to audit their books, make sure that they're meeting rules set out by the FDIC. If I want to transact, I need to create intermediaries. That could be a Visa, MasterCard, that could be an e-check system, ACH, or that could be a FedWire system. With blockchain, I don't need that. With blockchain, I have a known, described, and verifiable monetary policy. With the US dollar in this example, we have the Federal Reserve that somehow works with the Treasury to buy bonds, to create new money based off of what Congress decides they want to spend, and somehow that creates a monetary policy that gives us a relatively stable dollar over time, but isn't sort of deterministic, is inherently inflationary. With blockchains, we can introduce smart contracts. So instead of having to have third parties and sort of legal systems adjudicate contracts between parties, we can just use a bit of code. In the traditional system, we have these institutions, hierarchies, and subjective people that have to participate against the laws that are made by the legislature to be able to have a two-party contract. So when we talk about the anatomy of the blockchain, blockchains are actually far, far simpler than people make them out to be. In the very short form, they're a hash-linked list. They're a hash-linked list with a crypto-economic incentive that is a solution to what is known as the Byzantine general problem. And the Byzantine general problem is essentially, how do I get a group of participants to cooperate if I don't know which of those participants are nefarious or potentially colluding? But Satoshi Nakamoto, one of the major things that he introduced was proof of work. And proof of work created a mechanism by which we can have digital scarcity, but also a mechanism to have cooperation in a Byzantine environment. So the issue that we have with blockchain presently is that we can only do about 10 transactions per second on a truly decentralized blockchain that operates in a Byzantine environment. There's some projects out there that sort of centralize these solutions onto servers, and then we create points of trust, and we lose sort of these properties of Byzantine tolerant systems that make essentially perfect money. So the big question of the day then is, how do we make these systems scale? And the first thing that we should address is, what are the scaling requirements? So a lot of things try to address one of these things or maybe two of these things, but I have not seen proposals that manage to address all of these things holistically. So we need to be performant. So if we kind of say, what is the requirements for performant? If we look at card-based transactions, there's about 227 billion of those per year worldwide. Half of transactions by consumers were done with cards. So we go from about what would be 8,000 transactions per second to 16,000 transactions per second. And if we add some margin, if we want to create sort of a worldwide money system, we should be aiming for something that can do about 50,000 transactions per second. We also need the system to be verifiable. Blockchain uses mechanisms which are well described and demonstrated, such as cryptographic signatures, hash-linked lists, and Merkle trees. Most importantly, though, it still needs to remain Byzantine fault tolerant. So if we shard data, we can't necessarily shard consensus, and if we can't necessarily shard consensus, and proof of work is the mechanism for not sharding or for creating consensus, we can't shard the mechanism of work. It has to be economically sustainable. So in the long run, the incentives have to be such that the chain is essentially generating enough revenue to sustain itself, else you'll get an infinite inflationary system. And then the last thing I didn't add to this slide, but I would say, is that when you start sharding things, you need to make sure that they remain fungible. So every asset should have effectively equivalent value no matter where it sits within the sharded state. So what are the technical scaling bottlenecks of blockchain? If we look at Bitcoin, it's actually bandwidth. A lot of people say, oh, it's the work algorithm. It's all that mining power that's going into creating blocks. But there's really two things that miners are doing. They're processing transactions, and then they're doing work on those transactions to include them in blocks. The processing of transactions is actually not like a computationally intensive process. The work is required because it provides a mechanism to convert something of value, energy, into essentially a bet, which is the mechanism for how we create a Byzantine fault-tolerant system with nefarious actors, because people are essentially putting up money against what they're saying is the truth. But the real limitation is, how do these nodes come up with a consistent set of transactions to operate on? And in Bitcoin, 1 to 300 times the bandwidth is expended per unit of data that's actually committed to the blockchain. So if I commit 1 megabyte to the blockchain, the average node took 100 to 300 megabytes of communication traffic back and forth to do that, and that's actually the true present limitation of blockchains. If we kind of go further down the stack, which I think are less critical, but still worth mentioning, I think the next most critical piece is RAM, being able to have a performant node which is holding state. So as state gets bigger, you'll need more RAM. Obviously, that can be optimized per application. Then you have permanent storage of the blockchain. And then at the very last, eventually you run into limitations of processing power. So what is BlockReduce? BlockReduce is a proof-of-work managed hierarchy of merge-mined blockchains called a braid. And so essentially each one of these things would represent a blockchain, but it's created in a hierarchy. So we have our sort of main root chain here called prime. We then have what we'll call a region chain, and we have a zone chain. Now, the highest difficulty is in prime, and the lowest difficulty is in your zones. So that means that the zones will have the fastest block times, and prime will have the slowest block times. A nominal example of what that might be is you could have a block time in a zone of 10 seconds, a block time in prime of, say, 1,000 seconds, and a block time in a region of, say, 100 seconds. So each level, as you go up, maybe gets 10 times harder in its difficulty. But the important part of this structure is that we don't shard consensus. So the key to not sharding consensus and to not creating these sort of zones of trust is merge mining. So every block header in this architecture looks like every other block header in this architecture. So a block for a zone contains some superfluous data that could potentially have also been useful if that header had been found as a prime block or had been found as a region block, but is essentially superfluous data in the context of only being found as a zone block. But in doing that, I can make my zone miners simultaneously mine my regions and simultaneously mine my prime, so I'm not actually sharding proof of work, which is very important if I want to maintain a Byzantine fault-tolerant system. And in terms of data sharding, we can optionally shard data. If I have a lot of hash power, I would be economically incentivized to store greater amounts of the holistic state of the system, because I would be mitigating my risk and shortening my time to finding essentially nefarious blocks. If I am validating a smaller set of transactions and I'm getting these hashes from my peers that have already been, work has been done, I'm not necessarily just taking it on faith that that exists, because they're presenting incremental work to me, so I can take it on as much faith as the work is that they present relative to my economic context of me needing to know that that's true. So I could, as a zone, just look at other essentially peer zone transactions and not need to look at other region transactions or not need to look at other prime transactions. But if I have lots and lots of hash power, I would be incentivized to do all of those things, because if I'm mining and I eventually figure out that there was a nefarious block, I'm going to be wasting more hash power. So just to kind of give a diagrammatic feel for this, so we have a zone finds a block, That block hash then gets pushed up into the regions. The other zones, find their blocks. This is all happening asynchronously, but, for the sake of my cartoonish presentation, there it is. The zone blocks, obviously, though, I would, statistically find 10, say, zone blocks in I before I found a region block in B because of the difference in difficulty. So some number of these zone blocks get rolled up, recorded as hashes in B. Then you start finding region blocks. Those region blocks get recorded as hashes in prime. And then you'd finally find a prime block. So segmentation and aggregation is essentially the solution to our bandwidth problem. In a traditional blockchain system, I have nodes. These nodes have peers, and they're essentially transmitting transactions on an open outcry basis. So if I have 100 peers, I'm going to hear about a transaction 100 times. And that's essentially where the inefficiency of the bandwidth usage comes from. But if I can group those transactions into sort of these subgroups, and then I can create a representative hash of that subgroup before I then communicate that to my peers, I can then say, okay, do you have this block of transactions? And all I'm doing then is communicating a 32-byte thing to represent, say, 100 or 500 transactions, and only when I get the affirmative, yes, I actually want that data, do I use that bandwidth to send that out. So instead of transmitting all transactions hundreds of times over, I only have to transmit those transactions hundreds of times over within the lowest level open outcry system. But as I move up the chain, I'm now transmitting hashes which have sort of compressed the data in the lower level blocks. So what that means is that within our network, the peers self-identify as a node type. So I would decide to mine in zone, in region A, zone I, and I would tell all my peers, I only want raw transactions that look like they're from region A, zone I, and I only want to hear about something in region A from a peering block, or say from zone J, as if only if they find a block which has aggregated those transactions up into a set, at which point I'm willing to hear those transactions, and then the same thing for regions. So we do open outcry at the lowest layer, and then you do essentially open outcry of aggregated compressed hashes at the next layer, and then the next layer. So what this does, though, effectively, is it breaks this relationship between latency and block size. So as block size starts to exceed sort of the average bandwidth of the network, latency essentially explodes exponentially, and that's our physical limit of transactions per second. But because I'm essentially efficiently using bandwidth as I aggregate transactions through the structure, I can break that exponential and create a linear system again. So here's an example of what one might implement as a header for BlockReduce. So if we're looking at prime, region, and zone blocks, they're apparently identical. The header size is 268 bytes versus 80 for Bitcoin, but it has the information for all block types. So it's important to understand that you don't know what block type you're going to find until you found that block, right? Because you're doing hashing and you don't know what that hash is going to come out as in terms of the difficulty level until you've done the hash. So that's why the blocks need to be apparently identical. And what that block header becomes is based off the difficulty that you ultimately find. So if I find a difficulty that meets my zone difficulty, I found a zone block. If I find a difficulty that meets my region, I've found a region block. I've also simultaneously found a zone block because I also met my zone difficulty. And if I found a block that meets the prime difficulty, I've found all three. So what does that look like? If I'm finding a zone block, the information in purple is pertinent. The information in white is effectively wasted. If I find a region block, the information in blue is pertinent. The information in white is not completely wasted because I also found a zone block. And then if I find a prime block, that's the pertinent information, but there's no wasted information because I almost simultaneously found a region and prime, or a region and zone block. So within this context of this hierarchy, we also introduce the idea of scope. So a transaction now needs to be located somewhere within the purview of this hierarchy. And so that's essentially a 2-byte number. You could have up to, say, 256 regions, up to 256 zones. And so every unspent transaction output is essentially specified to exist in one of those regions and zones. And then if I want to process a transaction using that UTXO, I have to originate that transaction from that region and zone so that state is consistently updated. But what that also means is that I only actually have to wait for settlement based off the scope of my transaction. So if I'm exchanging or spending a UTXO within a zone and that UTXO is staying in that zone, I only have to wait for the next zone block to be settled. If I'm sending a transaction from, say, zone I to zone J, and our common parent is region A, I would need to wait for the settlement of a region block for that transaction to be settled. And then if we have no common region parent, I would need to have it be prime scope, so I would have to wait for the settlement of a prime block. So there's a trade-off that is introduced between time, cost, and security. This exists in blockchains, right? We talk about depth of a transaction in a chain. That's essentially certainty that that settlement won't be reversed. The same thing exists here, except there's essentially more granularity to that settlement, but then also scalability because of obviously the structure. So incentives. So our incentive structure needs to be changed. So in Bitcoin, there's really only one incentive, and that incentive is, or there's two technically. The incentive is to hash, and the incentive is to process transactions. Hashing, because if I find a block, I get a Coinbase. Processing transactions, because if I process it, I get the transaction fee. That's not actually the optimization of a blockchain system, because that's not the one sort of service that the nodes really need to provide. They don't take into account network latency, for example. But by creating a system where we divide the rewards up between group and zone blocks, we're incentivizing people to self-identify into groups and zones. We can then also split the reward, and this is a proposed reward mechanism where we introduce this variable chi, which is effectively saying what percentage of my reward is going to rewarding work versus something else, in this case, network latency. So what this factor here over with chi is the factor that's essentially rewarding people for finding the lowest latency group to participate in. So just on the rewards, Coinbase rewards would be earned in each of the blocks, whereas fees would be pushed into prime blocks to prevent miners from sort of piling in hash power into a sort of popular zone. And so that gets us into the concept of load balancing. So we need to load balance the system both from the supply side as well as the demand side. Because if we have an imbalance in, say, the hash power, we have an imbalance in security. If we have an imbalance in the number of transactions or the number of people using a zone, we have a disparate level of utility, and all these things lead to disparate prices. So what we need to do is we need to create negative feedback mechanisms from the grouping mentality to cause people to, from both a user side and a node side, to balance hash power and to balance the number of transactions that are propagating in each region and zone. So to do that, the block size will be dynamically based off of network demand, but will be calculated for the entire chain, not a specific region or zone. So if a zone becomes popular, it will become full, and transactions will essentially start increasing exponentially in price. Users will then be incentivized to look for a less populated zone to figure out how to do their transactions. In terms of mining rewards, we need equal processing and security, so the region and zone difficulty will be modulated such that the block target times will always be the same. So if hash power leaves essentially one zone, the difficulty is going to drop, which means if I'm a miner, I would then be incentivized to go back to that zone because my reward per hash has effectively increased. So it's this economically incentivized auto load balancing from both the supply and demand side. So then we look at Byzantine tolerance. So how is BlockReduce still resistant to what we'd call the 51% attack, even though there's sharding? So if we think about hash power distribution, and we think about the average blockchain system being able to do 10 TPS, I would argue that because of kind of how we're sharding the network, we would actually realize much lower network latencies because groups would generalistically form based off network topology to minimize latency, which means a system could potentially be 5 to 10 times more performant than that at the base layer. So one of these chains, instead of doing 10 TPS, maybe they do 100. But let's say worst case, nothing gets better and we have 5,000 zones. That means that only 0.2% of the hash power would be in any given zone. That means that to essentially execute a 51% attack on a zone, you would only need 0.1% hash power, which is insane. But could you actually do that? And the answer is no. And the reason it's no is because the large miners would be incentivized to have greater scope of the chain. They'd be incentivized to make sure that they're validating as many transactions as possible. And that process would create quick identification and cascading of non-nefarious hash power into what was either a non-nefarious fork or a nefarious attempt at including a transaction. And so as we get more scope, we'd end up getting more hashed, and contentious blocks would be adjudicated by more and more hash power. So additional items for thought that we're looking at are this concept of being able to have different node types, dynamic control of block sizes, how do we efficiently restructure. So initially, you don't want to have sort of this infinite number of zones. You want to have just enough zones to meet your needs economically, because the more sharding, the less utility. So you want to shard minimalistically based off of demand, but that means that as demand increases, you need to grow your number of shards over time. Economic and geographic groupings, looking at how do you deal with transaction rent, potentially having a mechanism by which UTXOs can be managed as accounts, the introduction of block interlink layers for compression of long-term chain state, as well as state trimming, use of Merkleized abstract syntax trees to interface with ZK snarks so that you can create your computational layer in a level 2 rather than having to use something like the EVM where everyone has to process a smart contract on all the nodes. So that was BlockReduce. I am currently working with Sriram as well as a group of undergraduate and graduate students to essentially make an implementation of it based off a Bitcoin code base. We're always open. It's an academic setting to people who want to participate and learn, especially if you're willing to come and learn blockchain and code. So. Any questions? I think we can hear you.
So when you first talked about the grouping model or the zoning model, it sort of looked like there's an opportunity to do kind of the geographic model. And some of it looked like just intellectually or academically it was sort of taken from some of the LDAP or X5, 2.5 directory replication models where you sort of collect nodes together to share data and then they basically move data between bigger groupings.
Yeah.
You later then talk about how economic or geographic topology in here might be something you could investigate. So can you talk to sort of your thought on that initial BlockReduce zone modeling and the scope of like the global footprint? Is there any kind of geographic component to that?
So every good distributed system isn't prescriptive, it's incentive based, right? So the real incentive is to pay nodes for lowering their latencies and becoming more network performant. So we're not saying that like this is the geography or this is what's going to happen in terms of things, but if you think about what would likely happen, zones will form based off economic groupings as well as network topologies and some mix thereof. So you could have a group that's strictly sort of an economic group that's kind of spread out throughout the world, but because of that sort of performance to latency, you'll likely see network topologic groupings which may reflect some degree of geography. But it's really up to the nodes and the users to kind of figure that out.
That makes sense. What I heard you say is that, graphically, there's a large number of transaction mining going on in, let's say, the U.S. and then Australia. You'll have sort of normalized zones there based on the economic incentives.
Yep. Yeah, and they're not going to be perfectly like monolithic, right? They're going to be somewhat sort of overlapping, enigmatic, and transitory over time. But yeah, it's self-optimization.
I think one of the other things that will impact and perhaps help it is that we're going to be going more towards direct links, radial type linkages down to the nodes. So, and there will also be algorithms to help dynamically.
Yeah, so I mean, there's certainly from a node-to-node standpoint, there's optimizations in how nodes peer and how nodes sort of interact and transmit data. In terms of structure, the issue that you run into with the data in the blockchain is that we have to have this temporal consistency, and we have to create a mechanism for having global consensus. So I guess you could call it radial if you wanted to.
You get better, much better response with a direct link. Some software.
Yeah.
Network, dynamically defined network.
Yeah.
Things like virtual reality or immersive technology.
Right. Yeah. So there's two aspects to it. One is sort of the data layer, and one is the consensus layer. So I think the question is, are there sort of further optimizations that could be had by, leveraging, optimizations that are used to optimize networks in other fields, like. Yeah, no, I think that's definitely something that can be done. I'm just saying that there's a difference between essentially how the data is propagated and how the data is mined and stored. Certainly there's improvements for how that happens.
Can you talk a little bit about some of the use cases, where you guys are with them, and what kinds of use cases you're looking for, so we can kind of get a little deeper into that?
Yeah, so generalistically, I think the thing that we're shooting for is, when we talk about blockchains, we talk about use cases. If we go back to my first slide, I said that they're value, not information, right? And so the real sort of killer application of blockchain, certainly in what I would call layer one, is money. So I think that's really what you're targeting, and what we're targeting is to create a system that's scalable up to human commerce, right? So not necessarily machine-to-machine transactions, but like if a human economically represented entity wants to interact with another one, they'll be able to do it using this agnostic system globally. Now, that being said, right, because this is a blockchain, because we have these basic functions like hash locks, because we can introduce something like masked, Merkleized abstract syntax trees, those create hooks for building layer 2 applications where we can use something like a ZK snark, which is trusted distributed computing, to hook into one of those layer 1 links to create smart contracts without having to have this sort of global, Ethereum virtual machine in the case of Ethereum.